Alright, so let's look at some of the more challenging questions at the end of the moment's tasks, starting with this one where we've got the open bonnet of a car held at 60 degrees. And we've got some various dimensions which we'll get to later on, and the centre of gravity of it is at G, so here. So first it wants you to draw and label the two other forces acting on the bonnet. So from the centre of gravity you would have the weight force of the bonnet due to its mass, and like we've talked about in previous questions, there's going to be a reaction force at the hinge, and these two forces are both vertical, so there's only going to be a vertical force at the hinge in this case, so keep it in equilibrium. So those are your two forces. Okay, so it wants us to take moments about O and show that the vertical force V is 9.7. So the tricky part of this question is finding out the perpendicular distances. So it's a bit rough, but let's sketch some triangles on here. So essentially, to get the distance perpendicular, so these forces are acting vertically, so the perpendicular distances are going to be horizontal. So essentially we want this distance and we want that distance in there. So using some trig, you've got an angle of 60 in there. This side is going to be 0.9 cos 60 because it's the adjacent side, and therefore this one would be 0.9 sine 60 because it's the opposite to the angle. We're not going to need that one, but it's useful to note it. And then this side down here is going to be 0.35 cosine 60 because this length here is 0.35, so then this is the adjacent side, so it would be 0.35 cosine 60. Okay, so we've got our distances now, so we can set up our equilibrium condition. So we know that the sum of the moments is going to be 0. So clockwise ones which are positive would be V times by 0.9 cosine 60. That's positive. And in the opposite direction you're going to have the weight force times by 0.35 cosine 60. And that's going to be equal to 0 if it's in equilibrium. W is 25, so we can put that in when we rearrange. So we get V is going to be 25 times 0.35 times cosine of 60 divided by 0.9 cosine 60. So this is why a few people who got their perpendicular distances wrong ended up with the right answer, simply because your angles ended up cancelling out later on. But in the later examples, it's not going to be so friendly, so make sure you're getting those right. And when you calculate this value here, you end up with 9.72 yada yada yada, which is approximately 9.7 newtons. Okay, so that is that one there. So we've done the moments part, and it wants us to calculate the magnitude of the force acting on the hinge at O. So let's resolve in the vertical direction. So forces acting upwards, we have V and we have R. Acting downwards, we have the weight force, which is 25, and that's going to sum to 0. So then we can calculate, essentially R is going to be 25 minus 9.72 yada yada yada, which is going to give us a force of something around 15. What's that? We're going to get 15 newtons to two significant figures by essentially showing that the resultant force is 0, and we've used the sum of the moments is also 0. So those are the two key equilibrium conditions, and for the first time we've seen our forces acting, and we calculated our perpendicular distances at these angles. Okay, so let's have a look at the next question. So we're getting into some seriously spicy questions here. So you haven't even got a diagram for this one, so this is where we start off with. So we've got a trapdoor. So trapdoor, and we've got the horizontal direction here. So we've got an angle of 60 degrees. And you'll often find the angles are like 30, 60, 45, that kind of thing, because they have simple trig identities. And we've got a force that's acting perpendicular to the trapdoor. So a lot of people got this wrong when they were doing the question, and they put a vertical force in here. But the key thing is that the force is perpendicular to the trapdoor. Okay, so we've got that one. And we also has a weight force, which is going to be acting from the centre of the object. So let's call this distance here 2L, because we don't know what it is, but we know the weight force acts from the centre, so it's going to act from a distance of L. Okay, so let's take moments about this position here, because remember, we're going to have some reaction forces acting here. So we'll have a vertical one, and this time, for the first time, we're also going to have a horizontal one, because this force has a component in the horizontal direction, because if we split this up into its perpendicular vectors, we'll have one going that way and then one going up. So we've got a force to the left, so we must have a force to the right as a reaction force here. So let's take moments about A, because essentially by doing that we make the perpendicular distance of both of these forces 0, so we can forget about them. And what we have is, going round clockwise, we have WL cosine 60. So if you want to dot in your triangle there, we want this distance here, because that's the distance perpendicular. That's the adjacent side, so it would be L cosine 60. And then in the opposite direction, we have the force F times by 2L, because that's the distance perpendicular. And we can rearrange that to find F. So it's going to be WL cos 60 divided by 2L. So you can see it doesn't matter what length we picked, because it gets cancelled out anyway. So the weight force is 4 times 9.81 times cosine of 60 divided by 2, giving us a total force here of 9.8 newtons. Okay, and we also want the force at the hinge, so I probably should have left more space for this, because this is going to be a bit tricky. But essentially what we're going to do is we're going to be resolving like vertically and horizontally to solve those. So let's scroll a bit sideways so we can do that. So resolving vertically, so looking at forces only in the vertical direction, we have got to work out the vertical component of F before we can do anything. So we're going to need to use some similar triangles. So this angle in here is going to be 60 degrees, using your alternate angles. So that one's going to be 30, so that would be 60. So we've got F cosine 60 going upwards. We've got the vertical component of the reaction force going upwards, and we've got the weight force going downwards. And if it's going to be in equilibrium, that's 0. So we can solve that to find our V. So it would be W minus F cosine 60. So remember, F was 9.81, so times by cosine 60. 4.9 by whatever, 4.0 times 9.81 minus the answer gives you a vertical reaction force of 34.335. I'm not going to round it because we want the magnitude of the overall force in a second. So let's resolve horizontally and show that's an equilibrium too. So we've got RH acting to the right, and we've got F sine 60 or cosine 30 acting to the left. So that is the horizontal component of that force. And we can solve that to find RH, which is going to be 8.495, yada yada. Remember that R is going to be the vector addition of those two, so RV squared plus RH squared, and if you calculate that, we end up with a value of 35 newtons as the reaction force from the hinge by using the vector addition of the two components. So that's that one. So let's have a look at Archimedes' ship sinking method. So this one cropped up in an exam a couple of years ago, but it's really cool. Gotta love Archimedes, one of the founding engineers, really, and the whole theory behind levers. So it makes sense to have a question involving what he's done. Okay, so we've got a pulley which is being used to lift a ship. So let's deconstruct this problem a little bit. So a force is being applied here, so a force is going to be applied that way, and it's going to cause this whole lever here to rotate about its pivot. Essentially, that's going to cause there to be a force going upwards in that direction there, because it's going to be essentially in the opposite direction to this, because if it is pulled around that way, it's going to cause it to rotate, which causes that one to go up there. But to rotate this ship, we need to apply a certain tension such that its moment is going to cause the ship to rotate. And what we're going to do is construct a right angle triangle, 24 degrees. So the vertical component of the force from the pulling force via the moment is going to be, so essentially T is going, let's call this force F2 so we don't get confused. T is going to be F2 cosine 24. So essentially what it's saying is this vertical component must be providing the tension here. That's where the force is coming from. And we can relate F2 to F later on. So to start off with, what we need to do is work out the value of tension that we need to cause this ship to rotate. So we're going to do that by taking moments about P. So in terms of going clockwise, we've got 5W. Anti-clockwise, we have 12T. And it's on the about to start rotating, those are going to be equal to 0, so then anything greater would cause it to rotate. So we can get that T is 5W over 12, which is 5 times 3.4 times 10 to the 4 divided by 12. And let's plug that in. And we end up with a value which is 1.4 times 10 to the 4 newtons. So that's the value of T. So we can then calculate a value of F2, because it's T divided by cosine 24, and we get a value of 15.5 times 10 to the 4 newtons. So now we need to relate F2 to F. So because of the lever system we've got in place, we've got 2.5 F2 is going to be 8.0 times F, because essentially using the lever and these different distances is allowing us to use a smaller force to lift it. So F is going to be 2.5 F2 divided by 8.0, and let's plug those numbers in, which gives us 4.8 times 10 to the 3 newtons, giving that to two significant figures. Okay, so how did we get there? So some keys to remember with this. So first thing was identifying the direction of the force caused by this one, so realizing that it would cause a force in the exact opposite direction. Next was realizing we needed to look at the vertical component of this force, so we could calculate T, and we used moments to calculate what T was. So those were the strategies we went through, and here are the calculations to solve it.